Ning has over 15 years of experience in machine learning across multiple industries, including web entity search ads, online retail, and cybersecurity. He was a senior manager at Microsoft, leading search at Bing Maps Autosuggest. He managed Bing local search in France and Italy in the restaurant segment. Before this, he led the development of Bing as relevance platform and algorithm improvements, delivering paid search experience in Bing and Yahoo. Ning also had experience in developing malware detection and spam detection algorithm during his tenure with China's top security firm. So let's welcome Ning and hope you guys enjoy his talk.
Thank you for coming today. It's a great honor to be invited here to talk about AutoML. I'm a firm believer that AutoML as an emerging technology is going to change how we use AI in the next 5 years. But I do recognize AutoML so far is kind of immature. So in the last I'm founder and I'm co-founder and CTO of OneClick.ai. So we built this the OneClick.ai, as the name suggests, is itself an AutoML platform. So in the last 2 years, I and the rest of the founding team has been busy working on this platform, developing AutoML ourselves. We learned a lot about AutoML, and we have our own vision about where the technology is going to go going ahead in the next couple of years. So I want to share our vision. So the talk will be organized as an overview of AutoML and classify technology into different categories and also the direction that we are heading, which we use the direction of AutoML. This is the overview of our platform. So it's basically code-free tool for developing AI. So okay, that's part of the things. So why we need to use AutoML? Anyone with a real-world experience applying AI to industrial problems will be faced with a couple of challenges. First of all, most businesses simply don't have the expertise. They cannot hire the right people, especially people with experience. So with the increasing demand on data scientists in the last couple of years, it's increasingly difficult to find the right people. Don't think about it. I know lots of people from with IT background coming from IT companies or internet companies. So you think hiring data scientists is kind of easy. But think about most of the businesses in this world have nothing to do with IT or internet. Internet probably just a selling tool, a channel for them. And even very large ones, with hundreds of millions revenue or billions in revenue, don't even have a data scientist. But in the nature of AI development it's very difficult to predict the results of an AI project. So basically, without actually building the model, without actually completing the development cycle, you have no idea what's going to be the result. Whether the performance of the model is going to meet your practical requirements, or how long it takes to actually get there is unpredictable. So that's why basically in nature, AI development is kind of an iterative process. It can last, each iteration can last a couple of months to half a year. That's a typical scenario from my personal experience. Because it's highly unpredictable, so actually most companies hesitate in applying AI. With my experience at Bing, at Microsoft Bing, even when we build new product, adding new features, we were hesitating using AI. So we started with rule-based first, and then in the next iteration we start adding AI functionalities. So it's going to be a lot more challenging for traditional businesses to use AI. And even if you decide to use it, according to Gartner, last year, more than half of the AI projects failed in the industry. So the financial risk is quite high. So AI projects is a huge investment for almost every business, and most of them are going to fail. So if you are the owner of business, are you going to invest on AI? All those challenges can be addressed by AutoML if technology is mature enough. So with AutoML, because the process is automatic, so you don't actually need expertise to build AI projects. And AutoML typically completes the entire process in a couple of days. So no matter how many iterations you need, you can complete it in a couple of days, then you can afford it. You can explore new technology, try new ideas, and try to improve the models or application multiple times in 1 month. It's something that people can afford to try. And also, even if it fails in a couple of days versus failing in a couple of months or half a year, it's quite different. If the risk can be taken. Okay, so exactly what's AutoML? Here I'm just using a definition from academic conference. It's actually SAML 2014. Progressive automation of machine learning. I know it's a very broad definition. It pretty much covers anything that automates part of the AI development cycle. And that's why basically you will see there are lots of technology claimed to be AutoML. They are, but they automate the process to quite different degrees. So we'll make a comparison about different technologies. AutoML has been drawing attention from academia in the last couple of years. Last year alone, I noticed I found 6 workshops and conferences focusing on AutoML. So compared to 2 years ago, I think there was only one SML was talking about AutoML, no one else. And also IDC predicts that in 3 years, AutoML will grow into about 1/5 of the entire machine learning market. That's huge, considering it's an emerging technology. I know that this kind of projection is mostly a belief. It's predicting the future without much data, but that's what people think. Also, there are lots of players, particularly in the US and in China. Most of those players emerged in the last 2 years. I'll talk about some of them. And finally, how the market recognizes AutoML. So here's the search trend for the word AutoML. Since mid-2017, I think the search has been increasing steadily. You must have noticed that there are specs. The specs are largely caused by Google announcement about their AutoML projects, even before the product was launched. Okay, so now let's actually talk about AutoML technologies. So I organized the entire talk into 2 sections. So automated machine learning, here I'm referring to traditional machine learning technologies, like a decision trees, that type of thing. And we also have another section talk about automated deep learning, which is actually our focus. So this is the general framework for traditional machine learning. You have data clients. So basically, once you have data, those are the steps you have to go through to build a model. So that consider it's a single iteration in the development process. You need to do data cleansing, feature extraction, and feature selection, and then select the model and do the hyperparameter tuning. Those are the typical things you go through. Here the point is, for each step you have many different options. I will give you some examples for those who are not familiar with this. So, for example, depending on your data type, there are many different ways to process the data. For example, just as an example, I'm not going to drill down into this, but for example, text. Maybe just simple natural language text, just the words we speak, but it can also be addresses or other structured information. So if you can detect the type of it, you can break it down by structure that allow you to extract more useful information. So as first step of any AutoML product, you need to import the data type. Actually, not all the products are doing this. Some of them just ask customers, ask users to provide the information. And also about feature engineering. So I'm not going to list all the feature engineering, but I want to emphasize on one thing called cross features. So that allow you to generate new features from pairs of features that are already defined in the data. Just some examples here. For example, for the text attributes, you can derive based on similarity or engrams or substreams. There are many different ways to define them. And if you consider there are multiple text attributes in the raw data, then the combination is huge. Of course, for the numerical data, you can do the same. And it's actually quite critical for some applications. Because the model, the traditional machine learning model you are using here, has limited ability to learn the correlations. So if you don't do those things in the feature extraction step, your model performance will be limited. But the challenge those technology brings is the combinations. There are huge number of combinations. The model cannot perform well with thousands of features. And actually, if you count all the combinations, it can be millions. So the next step, people have to find ways to reduce the number of features in your data set. It's called feature selection or feature reduction. There are quite a number of different technologies. You have to make your choices. So all that I'm saying here is in every step of traditional machine learning development, you have lots of choices to make. And for each attribute in your data, you have different choices. For text, for example, text attribute, it has to go through different steps to be processed. You can do spell correction, you can do n-gram, or you can use other technologies to process them. So you have, as a developer, as a data scientist, you have to manually make those choices. And the combination of them is almost infinite. So how do we make the right choices is a huge problem here. That's a process that can be automated. I'm not saying that all the AutoML technology is doing very well on all those problems, but those are where they're heading. Today, most AutoML platforms, actually, or technology, actually focusing on the relatively simple part of the problem. That's model selection and hyperparameter tuning. Model selection, because most of the technology actually using open source technologies, so they have, let's say, 20 predefined models that you can find in Python or R libraries. And then they just try all of them. But for each algorithm, you still have a number of hyperparameters to tune, so you have to come up with some algorithm to figure out the right parameters. So the common ones are grid search, random search, and Bayes optimization. Which one works better really depends on what model you are using and how many parameters you want to tune. But those are the common ones. And they are well defined and packaged very well, so it's kind of easy to build. So those are the technologies that I'm aware of in the AutoML space. They are using traditional machine learning models. I put them together in two dimensions. So the y-axis here you can see is how they do the parameter searching. The lower ones are using greater random search. That works well for a small number of parameters. And the upper section contains technologies that use model-based algorithms, including base optimization and reinforcement learning. So they work better if you have a huge number of parameters to search. But what matters the most is basically how broad those technologies can be applied to. So most of those technologies can only be applied to structured data. That basically means it's quite easy to understand because they are using the open source technologies, open source machine learning algorithms. They can typically only handle the structured data. To handle unstructured data, there's lots of feature engineering work need to be done. But unfortunately, the feature engineering supported by those platforms are quite limited today. To some degree, it's the nature of traditional machine learning. Doing feature engineering without really understanding what the data is and the problem you are solving is kind of difficult. Later, I will present the solution that we have. What we have talked so far is actually focused on the modeling problem, just how to build the AI models. But as AutoML is essentially a tool, you can still, so it also does data import, acquisition, and model deployment. And particularly on model deployment, there are a lot of things that can help you, improve the productivity. It handles the API serving, model updates, and does batch streaming, and handles the machine failure, that type of thing, and scales up when the traffic will use it more. Okay, now those are what we talked so far based on traditional machine learning technologies. But what's more interesting is the deep learning ones. Deep learning, I mentioned that traditional AutoML actually focused on structured data. To deal with unstructured data, we can simply switch to deep learning. But deep learning actually brings lots more challenges to this space. Let's take a look to how deep learning works here. Basically, on the data cleansing part, it's kind of similar to traditional machine learning. But when we do it manually, we actually do very little feature engineering today. We kind of just encode the data in a way that can be fed into neural network. So the focus of deep learning, when we design it manually, is actually to design a deep learning artificial neural network. The architecture and the parameters of this neural network decides the performance of the deep learning models. So the focus of a automated deep learning algorithm should be focusing on the design of the model. When we talk about the artificial neural network, lots of people think about this. This is very simple linear architecture. The model is designed layer by layer, and the the output of each layer is fed into the next layer as input. So that's a very simple one. That's how, technically, if you have more than one hidden layer, the ones in the middle, it's called deep learning neural networks. But it's not how we think about it today. Most of the models we're dealing with are actually non-linear architectures. This is DenseNet. It's an image classification model. It takes only one input, one type of input, a single image, which is represented as a matrix, and then fed into the neural net. But there are lots of connections between each layer. So that makes the entire model not a linear one. This is not over complex because you only have one type of input here. Think about it, if you have many different inputs. You have text, you have time series data, and you have images, you have numerical data all together, mixed. How do you design your model? You cannot even feed it into architecture like this. You have to design your model according to your data itself. So the technology to design neural architecture is called neural architecture search, or NAS. I don't know exactly the term was introduced, but it's getting popular in the last year. The basic idea is you have something called a controller. The controller is responsible for generating the architecture, or you can call it the design or spec of the neural net. Once you generate a neural net, you can train it as normal, just like an architecture designed by a human. Then you can evaluate the trained model on the validation set. The evaluation result, or you can call it the average accuracy or average loss, can be fed back to the controller. And the controller will update the model design accordingly. So, as you can see, the controller is the smart part. The key thing is it has the ability to generate the initial models, and then it must be able to improve the models, or not necessarily improve it every time, but change the models according to the feedback. In this process, you can see because we generate multiple models, it's an iterative process. So we have to actually build multiple models and train them on the real training data. So if we train thousands of models, it's going to be a very slow process compared to what we do manually. So if we design neural net manually, typically you probably design like 20, 40 in a year, and then you build those. You actually train those models and evaluate, iterate on your ideas. But if you do it automatically using your architecture search, you can build thousands of models in a couple of days or weeks. That's where its strengths come from. So there are basically two different ways to design controllers. The first one, some people call it a progressive one. Progressive neural architecture search. Especially, think about the entire search space of neural architecture for your application can be predefined. It's a finite space. And then you assign them a partial order. Basically, organize them as a tree. Then you can search all those possible models in certain order. And then all you need to do, if you use a greedy search algorithm, all you have to traverse the entire tree and develop each branch in the order that you have defined to figure out which to search for the better performing ones. You can start using heuristics, saying if this one is not worth developing, you want to develop it further. By doing this kind of pruning, you can reduce the number of models you have to train.
The other way to do it is using reinforcement learning. So reinforcement learning gives you ability to generate the model directly. And then you can, based on the model performance, the model performance can be considered as a reward and fed back to reinforcement learning. And it's causing the internal policies to change within the reinforcement learning model. Then next round, the model will generate a different design. So both there are active research in both approaches, but the same is right now academia heading the direction for the first one. It gives you more flexibility to control which model you want to control. Let's say it gives you the ability to reuse the model you just trained in the next model for performance gain. So in this space, compared to the AutoML players, there are very few deep learning AutoML technology has been built. The most prominent one is actually Google. I think early this year, right? Early this year, they announced a cloud AutoML supporting 3 different applications: voice recognition, translation, and image classification. There are also AutoKRS, the open source project that's actually more flexible than Google Cloud AutoML. Of course, because the open source technology doesn't handle the deployment. It only the only thing that does and it does pretty well is to build models. So OneClick.ai, the platform we developed, is the only other major player in this space. The difference between us is so far all the published research and the other products are all focusing on application-specific solutions, which basically means if you have, for example, let's take Google as an example. You have different algorithms. You have to write different code essentially for each different applications. For image classification, the solution is totally different from translation. And the one used for translation is totally different for voice recognition. Why? That's because all those solutions depends on human knowledge about the application, about the data you are dealing with. For example, for image classification ones, people have been doing research in this area for tens of years. We have learned which technology, which particular structure, architecture works, which doesn't work. So if we bring those knowledge into the search space, help us refine the search space, we can make the problem a lot simpler. We don't have to search all the possible neural net architecture. Instead, the search space is typically, let's say, kind of finite. So with enough resources, it's actually possible to enumerate all those models. Of course, they don't do that in total brute force, but without introducing those human knowledge, the existing algorithm won't work very well. Also, from this framework, you can see the controller doesn't look at the data at all. So the problem is, if I don't look at the data, think about controller as a human data scientist. If you don't look at the data at all, how do you even design an architecture that can take the data as input? The only way this can happen is because when they design the controller, they already know what's the data and what's the application. So they know the problem they are trying to solve. So when you have different set of data with different type of inputs and with different application, you have to design a new controller. That's the solution used by academia and by other products. But the problem of that is for every new application, you have to develop a new controller. That basically translates a simpler problem into a more difficult problem. Because in general, design a controller is harder than design a specific neural architecture model. And also, because it doesn't look at the data at all, even when it takes feedbacks, it doesn't look at the data. It takes, let's say, thousands of iterations just to observe any pattern. Because fundamentally, what the controller does is to figure out what kind of policy, what kind of structure that have you extract information from the data. And to observe, there are hundreds of structures you can explore, but you have to explore them all in order to figure out which one works for this particular data set. That's called start problem. So you cannot improve the model rapidly before you try it thousands of times. And also, think about this. Because you don't look at the data, the only feedback you can have is, let's assume to make it easier, let's assume the loss here I'm using is accuracy. It's a classification problem. So if the only feedback you are given as when you design the model manually is the average accuracy of your model, there's no other feedback to you, how do you improve your model? It's really, really difficult. As a result, the controller improves itself very, very slowly. So basically, let me summarize it. There are two fundamental problems. One is the application specific, to develop new solution, new controller for every application. Secondly, it's very slow because you don't have any information about data, and you don't have much information from feedback to learn. So, because we want to make OneClick.ai a general solution, and we cannot afford millions of machine hours to train those models. We have to make it really fast. So we are trying to solve those by building algorithms. So before we talk about how we solve it, so let's revisit the framework. So this is the traditional machine learning framework. We can turn it into a DAG. DAG basically means a directed acyclic graph. That's a uniform way to represent any, let's say, data pipeline. So the input data going through different processes and finally fed into the machine learning model that you have chosen. In the same way, we can represent the deep learning framework. The only difference in here, essentially, if you consider this as a data pipeline, the only difference is the inner structure of a deep learning model need to be okay. In the traditional machine learning, the entire machine learning model can be considered a single node in this graph. But deep learning models need to be expanded so that we can see the inner structure. But it can be represented as a DAG tool with the inner structure exposed here. So then we translate the entire problem into learning DAG or improve the DAG. Because once you come up with design for the DAG, you have a complete solution for an algorithm, whether it's a traditional machine learning model or a deep learning model. With this, what I'm saying is OneClick.ai trying to design the entire DAG altogether, just like in Google AutoML, they try to design the entire neural network altogether. This allows us to make sure the feature extraction or data preprocessing is coordinated with the model that you select, which is actually quite important. And also it allowed us to use similar algorithms to design very complex feature extraction process. But even with that, you still have application-specific controller, have all the drawbacks I mentioned before. So how do we solve it? The solution is very simple. We make the controller to examine the validation set first. So think about this. Validations for a data set, for a particular application, let's say we resolve a validation set of 1,000 examples. Then you have those 1,000 lines as input to the controller. Based on the data I observed, I can learn what kind of inputs you have and the characteristics of each input row and the correlations between attributes and labels. I can learn those things and use those information. I can design the initial model. When you have different validation set, the initial model will be different. That solves the cold start problem. And then the model is still going to be trained on the training data set, which is visible to controller, and validated on the same validation set. Because now the controller has seen the input of validation set. The feedback can be given for individual example in the validation set instead of the average accuracy. We can tell the controller the new model you just designed have the example A, B, C, but hers example D, E, F. That kind of feedback, that kind of granularity you have in the feedback helps the controller to learn much faster. So in the past, for every model you actually build, you have one feedback. You have a single feedback data part for the controller. But here, because I have 1,000 examples in the validation set, for every model I build, I have at least 1,000 data points that can be used to improve the controller. That's a lot faster than just learning from one data point. And most importantly, here the controller, we use the same controller across all the applications. That basically means if I have seen similar applications before, when you give new piece of data, we will start with a reasonable model because we have trained, we have learned what kind of neural architecture works for this kind of applications. And the applications are identified by the characteristics of its inputs. So, to summarize, this new approach works for both deep learning and traditional machine learning. And it works for neural architecture design and also feature engineering, and also data cleansing. Every single step is considered a node, just another node in the DAG. So we optimize the entire thing altogether, instead of just focusing on the model itself or parameter tuning. This method also makes sure the feature engineering we have chosen works well with the architecture that we end up with, because they are generated by the same controller. And because we have a lot more feedback data points to be taken by the controller every step, we can, instead of training thousands of models, we can build reasonable models in 20, 30 iterations. That's a lot faster than any algorithm that we know. To be frank, I have to say, in 20, it really depends on data and applications. I'm not saying that in 20, 30 applications, we guarantee that we produce a model better than any human can do. But from practical point of view, from our experience, in 20 to 30 models, we can find a solution that, let's say, about 80% time, we can find a solution in 20 to 30 iterations, better than human experts. Okay, then in the rest of the talk, I want to give a quick overview of our platform, basically how we use the technology. So we call this technology ABS. It's a foundation of the OneClick.ai platform. From there, we are able to do automated feature engineering and automated neural architecture search and model selection and parameter tuning. As I explained earlier, essentially those three things are done together by the alias engine. With those things, we have some unique advantage. So, for example, we are the only one that supports the mix of structured and unstructured data of any form. Right now, we support numerical and category data, text and image, and time series. We don't support, let's say, audio yet, and the audio video are not supported right now. But that's mostly about engineering efforts that we haven't put into yet. But still a setback. Also, because we optimize the model using these algorithms, most of the time it delivers better performance than humans. And we spend some significant effort to improve the time series models. And developing technologies to help us extract features, information from time series data and very complex time series data. I'm not talking about just a sequence of numerical data. I'm talking about a sequence of data that may contain multiple, multiple attributes. That really helps us to, the most popular application of our time series forecasting function is on sales forecasting. We are able to learn the, information from multiple series at the same time and see the correlations between the time series and the other factors that may affect the sales. For example, one thing we learned from our model is if customers run promotions, have sales target, and have discounts, those information, if provided together with the sales records, will help greatly on the model performance, because we will use those information to explain why the historical records going up and down. And also, we are able to see that the different products may compete with each other, so that we understand that when the sales of some product going up in future may squeeze the space for the rest of them. So, and those things are almost impossible to build manually because there's too many factors to consider. Okay, little history about our platform. So we started developing our platform in early 2007. Actually, a little bit earlier than that. So by the time we incorporated, we already developed the alias engine, kind of version 1. we have been working on its improvements since then. Last year, April last year, we got funded by Innovation. And then we started working on the UI and building other feature functionalities like deployment, that type of thing. So by the end of the year, we launched our private beta. And that time, we started selling our product to larger businesses. About 2 months ago, we released our enterprise version, which allowed us to do on-premise deployment. Especially finance and insurance companies require this feature. Otherwise, they simply refuse to do any experiments on it. Last month, we actually went public. So nowadays, anyone can go to our website and sign up to give it a try. So this is our UI. I have shown it before. The point is, this platform really requires no coding at all. You don't need any coding skills to build an AI model. And we also handle evaluations and give you different ways to analyze your data through our UI. Once you build the model, you can compare. Remember, we built the model iteratively. So you will generate a data bar, show you different models and their performance, so that you can choose the one that fits your needs. And the deployment of the model is just one click. So there's the API button, click it, you will get model deployed. And all the maintenance happens in the backend automatically. I would encourage everyone to sign up our platform. And right now, if you do using the promo code, you get the double tokens. Basically, you can run more experiments than regular users. Thank you. That's basically about this talk.
And then we have a 5 to 10 minutes Q&A with Ning Jiang.
Yeah, I think the problem is if you make the search space infinite, you need infinite compute to converge, right? So now, so one of the things that I missed here is, so are you looking at the data and more or less have a rule-based system which determines like which of the models you converge to, and then you are optimizing on the different hyperparameters, or like how are you constraining this search space? And the second question is, even with that, it needs a humongous amount of compute. So how do you plan to compete against Google, who can just scale its compute in modern day infinity?
The question is about the complexity of the applications. So the search space could be very, very huge. So it takes great computation resources to find an optimal model. So we certainly cannot compete with Google on computation resources. So we have to solve it using algorithms. We have to build algorithms that take, let's say, that iterate faster and converge faster to the optimal model. So that's why we say, we force our algorithm to take a look at the data before generating the first model. And all the feedbacks is also based on the validation data that we can observe. So once you can observe the data, think about how. Let me explain it by explaining how human data science works. So, as a human data scientist, you certainly don't just redesign your model based on average accuracy of the model you just designed. You will take a look on the validation side. You say which example got improved, which doesn't, and try to understand why. and then create assumptions. How about this saying, let's say, this kind of thing, kind of similar to the other work I have done before, and then maybe this particular substructure will work better on this piece of data. So you will introduce that kind of structure into your model and give it a try to see if it improves those examples that doesn't work well in the last time.
So this connection is still logical, like to reduce the.
Because we are building a general solution, so there's no human involved here. We cannot really build it using rules. We actually use reinforcement learning and using technology called policy gradient to update the reinforcement model.
Now, one last follow-up question on this. So then, are you targeting the entry-level market for, like, because experienced data scientist knows better. He can do embeddings, he can do cascaded models and all those things. So is it more targeted towards a market which has like more entry-level data science?
Depending on who you are going to call as experienced data scientists. So as I mentioned, actually most of our current customers, at least business customers, have a research team. Most of the time, about 80% of the time, to my estimation, the model built by the platform is better than what they have built in the last couple of years. So it's kind of similar to, when it comes to image classification, for example, those auto ML models are already beating or comparable to the best models that human was able to build so far, after so many years of research. The same thing happening in other applications. And because most of those applications are, let's say, business specific, they're based on their particular data. Even they have a research team, they have just a couple of people working on this. And the people comes and goes. So the investment on those applications is not as heavy as image classification. So that's why that actually help me. You don't have to find the globally optimal solution in order to beat them. Yeah. So I classify the entire AI applications in two categories, the head and the long tail. The head ones are, let's say, self-driving cars, face recognition, that type of thing. You can actually have a few talented researchers to build the best models, and there are finite number of models to be created for the hard problems. But there are huge long tail. Those long tails are more business oriented, solving problems based on individual business own data. No one can build models for them before acquiring their data. Those models, applications are built today by hand, by consulting services, or by their own team, by a small group of people. But the number of applications is huge. Think about very simple ones.
So in other words, time series data is one of the things that
yeah. Search forecasting is one of them. The kind of promotion I run is different from any other business. And the sales target I set, the discounts I set, and all different. And the products I'm selling are different. So you have to build a model, develop a model, a solution, specifically for my own scenario. And that cannot be solved by external research in general. So you have to have a custom solution for me. And the developing custom solution is super expensive. And without the right person, the model is not going to be optimal. And 1% of improvement in the accuracy of such model can easily translate into 1% of revenue increase. That's why basically this kind of technology is greatly needed in real world business. Yeah.
Okay, so we are going to have another Q&A session after the second part, the fireside chat. But again, thanks for the insightful talk. It's very impressive. And let's move on to the second part